Welcome to the deep dive. Ready to explore some seriously cool ideas? We're diving into the world of physics-informed neural networks, or PNNs. We've got this research paper, Physics-Informed Deep Learning, Part 1, Data-Driven Solutions of Nonlinear Partial Differential Equations.
Yeah, this one is fascinating. It's all about combining the power of machine learning with, the established laws of physics.
Okay, so I know a little bit about machine learning, but explain this to me like I'm 5.
Yeah.
How do you mix physics and AI?
Imagine you're trying to teach a computer to predict the weather. Traditionally, you just feed it tons of data, temperature, wind speed, all that, and it would, try to find patterns. But with PNNs, you can also give it the equations that govern how weather systems work, like the laws of thermodynamics and fluid dynamics.
So it's like giving the AI a physics textbook along with the weather data.
Exactly. It's like giving it a head start so it doesn't have to learn everything from scratch.
That actually makes a lot of sense. Does that mean it needs less data to make good predictions?
Exactly. That's one of the big advantages of PNNs. They can learn with much less data than traditional machine learning models because they already have like a built-in understanding of the underlying physics.
That's really cool. So instead of just finding patterns in the data, the PNN actually understands the rules of the game, so to speak.
Right. It's not just about correlation, it's about causation. PNNs can model the underlying physical processes, which makes their predictions more accurate and reliable.
This all sounds very theoretical. Are there any real-world examples of how PNs are being used?
Absolutely. One of the classic examples used in the paper is the Burger's equation, which describes how fluids flow.
Hold on, Burger's equation. Remind me what that's all about.
It's a mathematical equation that models things like shock waves in fluids or traffic flow. It's a tough equation to solve using traditional methods. But PNNs can handle it with remarkable accuracy, even with very little data.
Okay, I'm starting to see the power of these PNNs, but how accurate are we talking? What does that even mean in this context?
Well, in this specific example, the PNN achieved very low error rates compared to other methods. Essentially, it was able to predict the behavior of the fluid with incredible precision.
So are PNNs meant to replace all the other ways we solve these kinds of physics problems?
Not necessarily. Think of them as a complementary tool, especially useful when we don't have much data or when the problem involves complex shapes or boundaries. They're not a magic bullet, but they definitely add a powerful new weapon to our scientific arsenal.
That's a great way to put it. Now, the paper also mentioned something called continuous time models. What's that all about?
That's a really interesting aspect of PNs. Traditional methods often break down a problem into discrete time steps, like taking snapshots of a movie. But PNs can work with continuous time, like watching the movie play out smoothly in real time.
I see. So, like, the PNN understands the flow of time more naturally, like how things evolve in the real world.
Exactly. It's a more elegant way of representing physical phenomena, and it often leads to more accurate and stable solutions.
To illustrate this, the paper dives into another example, the Schrödinger equation. I'll admit that one's a bit over my head.
The Schrödinger equation is a fundamental equation in quantum mechanics. It describes how particles behave at the atomic and subatomic level.
Okay, so we're talking about the really tiny stuff, the building blocks of matter. What does the PNN do with this equation?
The researchers show how a PNN can learn to solve the Schrödinger equation, even with its complex valued nature and different boundary conditions. Essentially, the PNN learns to predict the wave function of a particle, which tells us about its probability of being in different locations.
So even in the bizarre world of quantum mechanics, PNNs can hold their own.
It seems so. The results are quite impressive. The PNN captured the intricate dynamics of the Schrödinger equation with high accuracy, showing that it can handle even the most challenging physics problems.
All right, so continuous time models, Burger's equation, Schrödinger's equation, we're covering a lot of ground here. But our deep dive doesn't end there. We also need to explore the other side of the coin, discrete time models.
You got it. And that's where we'll pick up in the next part of our deep dive.
Fantastic. I can't wait to see what other surprises these PNNs have in store for us. So we've explored that fascinating world of continuous time models, where PNNs can tackle these complex physics problems with a level of elegance that's, dare I say, beautiful.
Yeah, there's a certain mathematical beauty to how they handle time and space.
But as you mentioned, there's another side to this story, right? The realm of discrete time models. These are inspired by those traditional numerical methods we've used for decades, right?
Precisely. Think of those workhorse techniques like the Runge-Kutta methods. They work by dividing time into these smaller steps and approximating the solution at each step.
Right, sort of like creating a flip book instead of watching that continuous movie.
Exactly. And while these methods have served us well, they can be computationally expensive, especially for complex problems. PNNs, however, have found a way to leverage these discrete time approaches while boosting their efficiency significantly.
Okay, color me intrigued. How do they do that?
Well, PNNs can use what are called implicit run-Shikuda schemes, with a huge number of stages.
Mm.
It's some clever mathematical footwork that allows them to take much larger time steps without sacrificing accuracy.
So instead of flipping through the pages of the flipbook one by one, they can jump ahead several pages at once and still get the picture right.
That's a great analogy. And this ability to take giant leaps in time makes PNs incredibly efficient for solving large-scale problems.
Now, I'm guessing the paper has some examples of this in action, right?
It does. They revisited the Burgers equation using a PNN with this implicit run-Shikuda scheme and 500 stages. What's remarkable is that the PNN predicted the solution at a much later time in a single giant time step and still maintained impressive accuracy.
Hold on, 500 stages. That's mind-boggling. It's like predicting the outcome of a chess game after only a few moves.
It really highlights the computational power of PNs.
Mm-hmm.
This level of accuracy over such a large time step would be unheard of in traditional numerical methods.
So we've got continuous time models for elegance and discrete time models for efficiency. What else can these PNNs do?
The researchers also used a discrete time model to tackle the Allen-Cahn equation, which describes phase separation in alloys.
Phase separation, that sounds a bit like chemistry class.
Think of it as how different metals separate within an alloy as it cools, forming distinct regions. The Allen-Cahn equation models this complex process.
And the PIN was able to accurately predict this separation process.
Yes. It captured those complex dynamics, even those sharp boundaries that form between the different phases.
I'm sensing a theme here. It seems like no matter what physics problem they throw at it, the PNN finds a way to solve it.
That's a pretty good observation, and it speaks to the versatility and power of this approach.
But we've mostly been talking about these equations in the abstract. Let's get down to brass tacks. What are the real-world implications of all this?
That's where it gets really exciting. PNs have the potential to revolutionize a wide range of fields. One that immediately comes to mind is weather forecasting.
Now that's something everyone can relate to. How could PNNs improve our weather predictions?
Weather prediction is all about solving those complex systems of equations that describe atmospheric conditions. Traditional methods have their limitations, especially when it comes to long-term forecasting.
And I'm guessing PNNs could help overcome those limitations.
Exactly. PNs, with their ability to handle complex dynamics and make accurate predictions with less data, could significantly improve our ability to predict the weather, both in the short and long term.
So maybe one day we can finally trust those 10-day forecasts.
It's certainly a possibility.
Mm.
And it's not just weather forecasting. PNs could also have a profound impact on material science.
Okay, so from predicting the weather to designing new materials, how so?
Material science is all about understanding how materials behave at different temperatures, pressures, and so on. This involves solving equations that describe processes like heat transfer, diffusion, and mechanical stress.
Right, like predicting how a bridge will hold up under stress or how a new type of ceramic will withstand heat.
Precisely. And PNNs can accelerate materials discovery by simulating these processes with greater accuracy and efficiency. This could lead to the development of lighter, stronger, and more sustainable materials.
That sounds like a win for engineering and the environment. Are there any other fields where PNs could make a difference?
Absolutely. PNNs could also revolutionize drug discovery. Developing new drugs is an incredibly complex and time-consuming process.
I imagine it's like searching for a needle in a haystack.
It is. Researchers have to simulate how drug molecules interact with biological systems, which again involves solving complex equations.
And I'm sensing PNNs could play a role here.
Right. PNs could dramatically speed up this process by predicting how potential drug candidates will behave in the body. This could lead to faster development of life-saving medications and personalized therapies.
So PNNs could accelerate scientific discovery across a wide range of disciplines. That's pretty amazing. But I have to ask, are there any downsides to this approach?
Well, no approach is perfect. One of the challenges with PNNs is quantifying uncertainty.
Uncertainty. What do you mean by that?
Unlike some other methods, PNNs don't inherently provide a measure of how confident they are in their predictions.
So we can't be 100% sure how accurate their predictions are. That sounds like a pretty big deal, especially when we're talking about things like weather forecasts or the structural integrity of a bridge.
It's a valid concern, and it's an area of active research. Scientists are exploring ways to incorporate uncertainty quantification into PNNs.
So there's still work to be done, but even with this limitation, PNNs seem incredibly promising.
They are, and as research progresses, I'm confident that PNs will become even more powerful and reliable.
Well, I, for one, am excited to see where this technology takes us, but we've only covered the first part of this research paper.
That's right. We still need to dive into the second part, which focuses on using PNs for something truly groundbreaking, data-driven discovery of PDEs.
Data-driven discovery of PDEs, that sounds like we're entering the realm of science fiction. You're telling me these PNs can discover the equations themselves?
Believe it or not, they can. But that's a story for the next part of our deep dive.
All right, my mind is ready to be blown.
Well, get ready, because we're about to enter a whole new dimension of scientific discovery.
So in the last two parts, we saw how PNNs can solve some seriously complex equations, but now you're saying they can actually discover the equations themselves? That sounds like something straight out of a sci-fi movie.
It might sound like science fiction, but it's becoming a reality. The second part of this paper dives into how PNNs can be used for data-driven discovery of PDEs. It's like a total paradigm shift in how we approach scientific inquiry.
Okay, break it down for me. How can a PNN figure out a mathematical equation just by looking at data?
Okay, so imagine you're observing some physical phenomenon, like the movement of a pendulum. You collect a bunch of data on its position and velocity over time, but you don't know the equation that actually governs its motion.
So we have the data, but we're missing the instruction manual,
Yeah.
so to speak.
Exactly. Now here's where the PNNs come in. You can train a PNN on this data, not to just fit the data points, but to actually find a function that describes the underlying relationship between the variables.
So instead of just connecting the dots, the PNN is trying to figure out the equation that drew those dots in the first place.
Exactly. And to guide the PNN, you can incorporate some general physical principles, like conservation of energy or momentum.
So it's like giving the PNN some hints based on our existing knowledge of physics.
Right. And as the PNN learns, it essentially reverse engineers the equation that best explains that observed data.
That's incredible. It's like the equation is hidden within the data and the PNN is able to unearth it.
And the paper gives a couple of really compelling examples. One is the Burgers equation, which, as we discussed earlier, describes fluid flow. They generated data from the Burgers equation without explicitly telling the PNN what the equation was.
So they were testing whether the PNN could rediscover the equation basically from scratch?
Exactly. And the results were remarkable. The PNN successfully identified a function that closely resembled the Burgers equation.
Wow, so it basically figured out the underlying physics just by analyzing the data.
They also tested the PINN on the Korteweg-de Vries equation, or KdV equation, which describes waves on shallow water surfaces.
KdV, another famous equation, with those cool solitary waves called solitons.
Yes, and again, the PINN was able to extract the KdV equation from the data. It just demonstrates its ability to uncover these hidden mathematical relationships.
This is truly groundbreaking. It's like we're giving AI the tools to not only solve problems, but to understand the fundamental laws that govern our universe.
It has the potential to accelerate scientific discovery in ways we can only imagine. Right now, imagine using PINs to uncover new laws of physics, or to model those complex systems that we currently just don't fully understand.
It's both exciting and a little bit daunting to think about the possibilities.
It is. But one thing is clear. PNNs are transforming the landscape of scientific research. We're moving from a paradigm of deduction, where we try to derive equations from first principles, to a paradigm of induction, where AI is helping us uncover the hidden patterns and laws embedded in data.
This has been an incredible deep dive into the world of PNNs. I feel like I've gone from 0 to 60 in our understanding of this technology.
It's a rapidly evolving field, and we're only just beginning to scratch the surface of its potential.
Well, I, for one, am eager to see what the future holds for PNNs and for the future of scientific discovery itself. Who knows, maybe one day AI will help us unlock the greatest mysteries of the cosmos.
That's a thought to ponder indeed. Thanks for joining us on this intellectual adventure.
And to our listeners, remember, stay curious, keep learning, and never stop exploring the wonders of science.